Okay, welcome back. This is the 11th session of the part 1 of a series of lectures on stationary time series analysis with modern signal processing techniques. The topic today will be a bit interesting in the following sense. So right now, what we have is we have discussed some models for non-stationary time series, and we have introduced some algorithms so that you can see the dynamics, visualize the dynamics. It can help you to do some reconstruction and so on. But we haven't systematically discussed how to achieve the mission called decomposition. So today, the algorithm, the focus will be the decomposition. But before we achieve the decomposition, I want to rethink or reconsider the model we discussed in section 3 about adaptive non-harmonic model. And this is a reference which contains more details which you can read if you have interest. So just a quick recall about adaptive non-harmonic model. So what you do is you have multiple components and you replace the cosine function by one periodic function called wave shape function, WSF. And this is how the picture looks like. And we have several terminologies. For example, we can use Fourier series to represent the wave shape function and call this guy, each guy, the Eros harmonic, and so on. So technically, you can view Y as infinite components of cosine function. But the question we want to ask here is one wave shape function sufficient for real-world data? So in this, to discuss it, let's focus on one intrinsic mode type function. That is, if we only have one component. For example, in this signal, let's focus on the cardiac component. And if you pay attention, you may see that there are two blocks that I indicate. One, you have a small ear, right here. And the other one, there is no ear. Okay? Ear, no ear. Okay? And it tells you that, well, somehow the so-called oscillatory pattern, may not be fixed, may have some changes. But is it really true? Is this assumption or this observation really true? So let's take a look at this previous model, the adaptive non-harmonic model. You have A of t, S of V of t. And how to do the interpretation of this function. So S is what? It is one periodic function, isn't it? When you have one periodic function, you compose it with dilation. And this dilation, this is a phase function, and this is a monotonically increasing function, which will dilate S from time to time. And the dilation is the instantaneous frequency. And you do the scaling of the size of the oscillation by the amplitude. And this is the signal. And if you pay attention to this idea, it is a dilation of one pattern and the scaling. And if you want to use dilation, for example, of this pattern, you want to dilate it and scale it so that you can see this pattern. What should you do? There is a notch here, and there is no notch. So you need the amplitude modulation function to change fast in the middle so that you can catch this notch or dichrotic notch. But in the previous model, we need the amplitude modulation function and instantaneous frequency to change, not fast. If they change fast, then we lose the identifiability. And the algorithm may have some troubles. So this is the first observation. Let's take another look at another signal, where I show you another PPG signal, and this time I add some more information about the period, the inter-peak interval. And you can see the inter-peak interval gives you the pulse rate, and you can use it to study pulse rate variability, but this is not our concern today. Now, you see this is a dichrotic notch. And sometimes it has 1, 0, 1, right? Diacritic notch, and disappears. And well, it is kind of chaotic. It's hard to say if there will be any pattern. Well, sometimes it has one, sometimes it doesn't have. And in real world data, you will see something crazier. So again, we ask our question, what's wrong if we only use one wave shape function and do the dilation and the scaling? Again, the instantaneous frequency or amplitude modulation needs to change fast to capture this behavior if you only have one pattern. So maybe the adaptive non-harmonic model is not the ideal model. It's not ideal. We need to consider something different. And in general, this is more about PPG signal. PPG signal, people have kind of classified the signal cycle oscillatory pattern into 5 patterns. And this is the literature. You see, 1973, they already had some ideas. You see, there's kind of many different scenes. And when you have several different scenes, then how can you use just one pattern to describe? Oh, it is challenging. So again, the emphasis here is one wave shape function is not sufficient to model real signal. In particular, just one wave shape function via stretching and the multiplication, or dilation and the scaling. That is a real world data. And maybe you can say, this is real world data, right? So maybe there are some other information that we don't know, and this is a modeling problem. That's true. So let's take a look at this simulated example, and you will see why it is maybe something we really need to consider. So this is a signal I generated myself, and this is very simple. This is just some kind of 0, 1, 0, 1 bump function, and I put it in different locations. Okay, but the location Ti and the Ti minus 1 is not constant. It may change, be put in different locations, right? And you multiply by some amplitude modulation. Very simple simulation. And you can see by your eyes, it is a very nice oscillatory signal. Not a problem at all. But the appearance of the pattern is not constant. It's not, does not appear in a constant frequency. So now if you use this guy to model it, use this S is the G, right, and you have phi. What do you lose? You lose the dilation. The dilation part is missing, right? You lose the dilation. Or the instantaneous frequency has to be fixed over a period and change dramatically, fixed, change dramatically, and so on. Either way, you have troubles. You run into troubles. So this may not be, using only one wave shape function may not be the optimal solution. So the question we want is to ask, hey, is it possible we define a notion of time-varying wave shape function? That is, the wave shape function itself also depends on time, but not fixed. That is, there is more than one wave shape function, and this wave shape function may change in some way, like smooth in some sense. So this is the hope of the generalization. We want the wave shape to depend on time t. So what to do this? We can just focus on some, we can take a very simple observation, Fourier series, right? You have S and you have Fourier series expansion, and we have discussed this infinite sum before with some regularity, distribution, whatever it is. Now, we can rewrite y of t in this way. Easy. It tells you there's only one wave shape function. And to achieve the idea of capturing the time-varying nature of wave shape function, what we proposed before was, let's take a look at this guy. You have C0, CL, and alpha L. Those guys depends on the wave shape function. How about if we make them to be time-dependent? That is, we have multiplication, and we ask this guy to be BL, and this is the phase function, and now we ask it to be VL, and this is the trend or the constant trend. We make it to be another BL. So this is a generalization. And we certainly need some conditions that we will discuss in a bit. But in this formula, we still code this guy, the LO's harmonic, and when LO is 1, it's called fundamental component. The same idea. And the summary is, we have C0, CLO, and the alpha LO. They depend on time. They want them to depend on time, so that they can capture the time-varying wave shape function. And in practice, well, we just usually, for the identifiability issue, we just assume the wave shape function has mean 0. Otherwise, we may have contamination with the wave shape function and the trend. So we can just remove this part. Very good. So what will be the conditions we need for this generalized adaptive non-harmonic model? Actually, it's very simple. The first one is slow time-varying wave shape. That is the phi LO here, it should be very close to LO times phi 1 LO. That is, we want the instantaneous frequency to be really the multiples. Second, we want to have some capital N so that the higher order magnitude will be very, very small. It will control by epsilon. Third, and then second, we also need the slow time varying instantaneous frequency and amplitude in the following sense, which is just like what we had before. And we have multiple components, then we need, again, like before, some kind of separation of instantaneous frequency. And we need that the fundamental frequency of different components will not be the integer related, will not be related with integer multiples. Why? Because if you have, for example, phi 2 1 prime and the phi 1 1 prime, and this ratio is 3, then the harmonics of the second component will be merged or cannot be identified from the first component. They will be merged together. Okay, because of the first harmonic, you will have 1, 2, 3, 4, and this is 3, 6, 9. They will be mixed together, summed together, and you just get one wave shape. You cannot identify if there is 1 or 2. Okay, so that is a very critical assumption. We need non-multiple condition. Non-integer multiple condition. So this is an illustration of this model. Why it can help to capture, you see, notch. How to say if there is a notch, no notch, and the notch. How to quantify this guy. So this signal, if you decompose it or you rewrite it, you have 3 components: B1 cosine phi 1, B2 cosine phi 2, and so on. First 3 harmonics. And now, if you focus on this region and you compare with their phase, the phase of phi 1 and the phi 2, okay, and you multiply phi 1 by 2 and subtract it by phi 2, then you see it is time varying. And it varies a lot. It varies a lot. Okay, and then this is the unit of angle. So it tells you that the phase information of each harmonic actually encodes a lot of time domain information. And this phase information will be something we will discuss extensively maybe tomorrow. Yeah, it should be tomorrow or next week. Okay, and to achieve this decomposition, as we know, you can apply synchronous squeezing transform and plus time varying band pass filter idea. You can certainly apply other algorithms, but that is something we achieve here. Very good. So it tells you, okay, we have a new model, which is a generalization, which is more kind of reasonable for us to capture real-world data. But what we want is a decomposition, as I mentioned in the very beginning. Now how to achieve it? So the algorithm is called Shape-Adaptive Mode Decomposition, or SAMD. And this is the paper. The MATLAB implementation can be found in this QR code or this link. Okay, so what do we want? We have this signal, and as I told you, this is a formula, and there is noise. The SAMD algorithm will help you to decompose, obtain each component, and hence each amplitude and each phase. That will be the ultimate goal of SAMD. The idea of SAMD algorithm is actually very simple. It is actually a series of simplification of the originally very complicated model. That model is time varying, amplitude, phase, everything time varying, multiple components. Like, wow, it's kind of functional analysis, right? You need to estimate functions, which is in general infinite dimensional problem, very complicated. So the simplification here is trying to reduce all this functional estimation into parametric estimation. So first, we have some assumption. We assume we know how many harmonics we have. Okay, instead of infinite. If it is infinite, then there's technically really no hope. And this it's not really no hope, but we have to go to the part 2 for analysis. But now we're in part 1, and we need this assumption. And we assume we know this guy, and how to estimate this DI, there will be another topic we need to focus on. But we assume we know it, and it's finite. But still, even if we have this, there's still too many parameters. So let's make a further assumption. We assume that this BI doesn't depend on the harmonic. We just move it out. BI, okay, multiplied by CI. Very simple idea. Now further, still too many parameters, right? A further simplification. So what we do here is, first we have cosine 2 pi phi. Now we want to use this guy, but we don't want to estimate phi. We want to say, hey, we have only the fundamental component. We don't need to know all the harmonics. We only know the fundamental phase. And for each fundamental phase, we take the power of k. That is, we consider polynomials of different phases. And we add on some coefficients. And there will be some c and the d coefficients for sine and cosine to capture the global phase. That is, the global phase originally was captured here. But right now, we separate the global phase into 2 parts, cosine and sine, global phase. And for the phase itself, we use polynomial to fit. So right now, we reduce the problem into several parameters. Good. So once we have this guy, why do we can proceed with the algorithm? But before showing you the algorithm, why do we prefer to think about this form? The main reason can be seen from this example. If you focus on this synchronous squeezing transform, you see there's a lot of chunks, right? And if you remember, that's another reason we need this shape. And then you can see that there are a lot of interference in high frequency, high order harmonics. It's challenging to get too much. And there will be also spectral leakages and so on. So if you want to estimate things, it's challenging. But for the fundamental component, in particular for the lowest frequency one, you can get it relatively nicely. And now if you go to the shape, you can get each component, each intrinsic multifunctions, fundamental frequencies well enough back. And so that is why motivated us to use the instantaneous frequency and the global phase separate. Because if you use instantaneous frequency to estimate a phase, you lose the global phase. So that will be the overall motivation. So the SAMD algorithm is now just an approximation or optimization problem. We get a noisy signal Y, realization Y. We assume we can estimate the amplitude, BI theta, like before I mentioned. and we can get the instantaneous the phase of fundamental frequency up to global phase of each component. Okay, and now we try to fit C, D, E. So we reduce the estimation problem from the functional estimation to parametric estimation. And you see there is a very annoying cosine sign, so that is a linear regression problem. And what we need to do is trying to get a nice initial guess for all the coefficients so that we can conquer this nonlinear regression problem and so on. So what we do to get the initial nice initial is using the linear regression approach, which was proposed back in 2016. Assuming that there is only one wave shape function, and the idea is very simple. You have infinite many harmonics. You assume that's finite, right? And again, you rewrite the phase into cosine and sine, and then you run some minimization, optimization. Okay, where you know A theta k, that is estimated from synchro-squeezing, and the phi k, the phase, you estimated from synchro-squeezing, and so on. And then now you just solve this linear regression problem. You can see the regressors are those guys. This is a regress A tilde k t times cosine. This is a regressor, and this is the coefficient. So this is a linear regression. You can solve it quickly. So you get all the C and the D, and now you can get the decomposition of each harmonic. But again, this is under the assumption that there is only one wave shape function, so the performance is certainly not good. But it can serve as a good initial guess for the nonlinear optimization problem. So the overall algorithm is like the following. You run linear regression, okay, and then you run nonlinear regression using iterative reweighted least square algorithm, which you can easily find in every language nowadays. And then you minimize this time. So in the MATLAB code I share with you, there's only one line or two lines to implement all this. Oh well, sorry, this nice, but you need to run, for example, synchro-squeezing, ridge detection, and reconstruction of each blah blah blah. So, but the code is short actually. So let me show you the result. Okay, this is the algorithm, very simple. Now let's see the result. I give you two signals, two components. You can see the wave shape changes, right? Easy to see. Okay, and this is summation. And there's some noise, very small noise. Now if you use SAMD algorithm to do the decomposition, you can get the two components back. Okay, and there's a gray band that is just the standard deviation of the 100 realizations of the noise. Now you can see you can capture scenes back reasonably well. I will not say perfect, but it's reasonably well. You can get the wave shape. Okay, the dynamics. You see this small part is captured. Small part is captured, which doesn't exist in the beginning. But if you use linear regression, you see the wave shape is fixed everywhere, right? So it is very, very fixed. Although the oscillation is okay, but you lose details. And we also compared with existing other algorithms. For example, this RT-BR or MMD. They published around 5 years ago, 6 years ago. And you can see the result is reasonably well, but you do this MMD is kind of a bit crazy because the algorithm is maybe not very robust to noise, and this one is reasonably well. But you can see the wave shape is fixed. So this one, this RT-BR, actually depends on a fixed wave shape function, and this depends on time varying wave shape function. But AMD seems to be more, give you a slightly weird result. And you can find the code. You can find the code online. They share all the codes. And this is the noise level versus Rubin square error. You can see that MMD's error is usually the largest one, and the SAMD is relatively small, but it becomes weird when noise is very large for the first component. But overall, it's comparable. And when noise is big, actually, LR, linear regression, and the RDBR seems to perform relatively well because they assume a fixed wave shape function, and this fixed wave shape function, the details is kind of masked by big noise. That's one reason. And that is computational time, which you can see SAMD is in the middle, not too bad. And the RDBR is faster because it assumes fixed wave shape. Linear regression is very fast, and AMD is very slow, and usually it doesn't converge. So it has, sometimes it doesn't converge. Okay, and this is a comparison of different types of noises. We consider different types of noises, and that is the result, which shows you that actually the algorithm is quite robust to different kinds of noises. And this is the result when you have three components. When you don't have noise, this is the ground truth, and this is the result by SAMD. You can see you can capture almost everything, and then this is linear regression. Again, you lose the local details because the wave shape is fixed. And the RDBR, the same as local linear regression, it loses local details, but it generates some strange errors, right? Strange spikes. And AMD in this case performs quite well because it's no noise, but still it has some deviation from time to time. And when you have noise, you can see the similar result, the same trend. And this is another summary statistics of different noise level versus root mean square error, and you can see you can see a similar trend as before. And then, what's wrong with this? Okay, now this is there are some real examples. So this is a cardiogenic artifact. So this is a respiratory signal. And if you use SAMD to do decomposition, you can get the respiratory signal and the cardiogenic artifact. Okay, you can see the wave shape does changes. But local linear regression, RDBR, the wave shape is fixed. But I have to say this RDBR is not realistic. All respiratory signal cannot have this spike. And this MMD is okay, but it has a lot of strange spikes in the end, which is, again, not very physiological. And this is the EEG signal. You can see this is the EEG signal for a patient suffering from epilepsy, and this is a decomposed signal using SAMD, and the decomposition using RDBR or AMD. It's okay, but you also always see some kind of small strange things, which is difficult to interpret. And this is the ECG signal, easier for us to interpret. For example, RDBR, that is totally non-physical. Local linear regression also has this trouble because it has to adjust to time varying wave shape, so you see some artifacts. But here, you see something better, and there are some small artifacts there. And if you look at MMD, you also see something crazy. Okay. And this is the decomposition, which is not very ideal. Okay, and this is the signal quality thing I showed you before, and that is, I promise you to explain how I achieve this decomposition. And this is how I achieve the decomposition using SAMD. So you can see the PVP signal, and this is decomposition, and this is how we define signal quality index. And this is another decomposition of PVP signal. Okay, if we run it, you can get the cardiac component and the working pattern. Okay, now you can do the analysis of each component. And this is another example, which shows you that using SAMD, you can do quite a lot. I think that is the end of the slide. Thank you very much.